We started talking about safety and we covered the Bhopal accident. Today we'll be talking about inherent safety. The person who actually proposed this as a concept was this man, Trevor Kletz. Trevor Kletz is considered to be one of the greatest chemical engineers. He wasn't really a chemical engineer, he was more of a chemist, but he has been treated as a chemical engineer. Usually people didn't make so much of a distinction between the two because roles were quite complementary. So Trevor Kletz was initially a scientist, and increasingly he got interested in the area of safety. He was working in this company ICI, which was the largest chemical company in England and also among the largest in the world in earlier days. It was a very big company and spanned a whole lot of different kinds of products. You may, of course, know some of them like Perspex, Dulux paint, polyethylene, the people who invented polyethylene. Presumably, there were a few accidents, and he got deeper and deeper into understanding why do these accidents happen. He compiled his ideas based on what he found, and he wrote a very influential paper which is called "What You Don't Have Can't Leak." I'll send you this paper. It's very easy to read. You can read it. What he said sounds very obvious, that what you don't have can't leak. So effectively, I mean, if you look at the Bhopal accident and you say methyl isocyanate, if you didn't have methyl isocyanate, it wouldn't leak. It's as simple as that. So the question is, obviously, there must be cleverness associated with being able to achieve end objectives and yet to also have that kind of an inherent safety so that you don't have, when you say what you don't have, you can qualify it by saying what you don't have too much of. I mean, that would be another way to state the thing. Kletz is also the person who introduced what is known as HAZOP, hazard and operability studies. You'll learn this, I think, in your subsequent years when you cover some processes and safety in more detail. What he tried to get rid of are surprises. He said that these are not surprises. This is just that we didn't really plan for things well enough. And so we didn't identify the hazards. We didn't identify the risks associated with the hazards. We didn't have a look at how really to mitigate the risk. And then you have an accident and you say, oh, we had a terrible accident. You're asking for trouble. Okay, that's basically what he was trying to say. That's why he's considered as one of the greatest. And in fact, he's called, these are among the few chemical engineers who are considered to have changed the world. Changed the world, of course, for the better, I suppose, most of the time. Later on, they had another survey, and I think he was among the 10 chemical engineers who changed the world. I mean, they narrowed it down. Okay? So that's the level of greatness that is associated with his work. Now, what did he actually say? As I told you, he proposed this concept of inherently safer processes, what also you can call as inherent safety. Effectively, the objective was to achieve inherently safer design for the plants, and it was around 1991. So you're talking about around 30 years ago that this was mooted. So not too long back. And as I said, most of these things happened because they were presumably serious accidents. Now, the things that he says are very obvious, actually, in hindsight. One is that he says minimize. What he's trying to say is that if you are working with a hazardous material, well, it may happen that the chemistry is such that no one has come up with a better material to work with, And so you might be compelled to work with hazardous materials at some times, but perhaps there is an opportunity to minimize. So what he says is reducing the amount of hazardous material present at any one time, e.g. by using smaller batches. That would be one way to do it, that you have more repetition of batches, smaller batches rather than one large batch. There are other ways also of achieving this we will discuss. Substitute. Substitute is where you can possibly replace some material with a less hazardous material. If you can do that, nothing like it. I mean, that's the best thing to do. For example, it would be quite common, especially in laboratories, when you have, you're doing organic synthesis, etc., and your flask is kind of coated with some tarry material, and people would just pour in some solvent into it, and this tarry material would dissolve, and you pour it out and pour it into the drain, or probably into another storage vessel, and later on it might have been incinerated. Okay. In many cases, I'm not saying in all cases, you can actually just use a good detergent and water and achieve the same objective. It's not that you'll always achieve it, but there could be many cases where you can. And so there would be little justification in using a flammable solvent just to wash out your stuff. And you can imagine how many times that whole thing gets multiplied when you try to do these things in a big plant. Obviously, substitute is a very important principle. Another is moderate. Many times what happens is, like, unnecessarily we might be working with concentrated acids when it's not required. Even a dilute acid might do the job. So there is a way to moderate. Say, for example, if you're working with a gas at high pressure, maybe there is a way of cooling, have a cold liquid instead of a gas at high pressure. This would be another instance where you could actually apply this principle. Okay. Simplify. Now this, to me, I would say is one of the most important. I find this happening all over the place, where you actually, your basic chemistry or the design may not be so great, and what you do is it leads to some problem, and then you put in some solutions to that problem, then that in turn creates some problem. Again you have another line of defense against it, and what happens is that increasingly things get more and more complicated. It's not very different from if you tell a lie, and then to cover up that lie, you're telling another 100 lies, something like that. Whereas if you were honest enough and said, hey, what I said is not correct, it's I'm sorry about it. That's it, matter ends there. Similarly here, one can just ask, then why are you doing all this? Can't you do it in a different way? There is something very strange about human beings. Some people really do like to simplify. They like things simple. And then there are other people who like things complicated. You go and there are visitors, and you take them to your plant, and you tell them, this is the plant, you look at it, you're filled with awe. It looks so awesome, so huge, big, and impressive and grand. Or I used to find, even in when people used to like write the mechanism of an organic reaction, and you'll see this arrow, this atom going here, and then there's another arrow from here to there, the bond moves, and the more arrows you write, the more impressive it looks. In fact, the papers also, you're impressed by these arrows many times, and more sophisticated it appears. I mean, it's more impressive. But another person might say, well, you don't need all this. It just goes like this, and in a simple way. Probably that guy's paper will not get published. It looks trivial by comparison. But obviously the second person a much greater person. Okay, in not that first one. Okay, but again, I mean, this is the way things have happened. Okay, and so I'm just saying that it's not just restricted to plants and processes. There is something about our mindset which is different, and everyone is not tuned the same way. There are also two further principles that came later on. One of them is error tolerance. No, I mean you'll find there are people who cut things too fine. They're just not leaving any room for error, assuming that that's enough. What do you need? It's not very different from if you're sleeping and you have a bed sheet. The question is, how wide do you make the bed sheet? I mean, there are some people who will make it not very wide, and so if you're tossing and turning a bit, your bed sheet is not on your body. And then there are others who will keep enough of a margin that whichever way you turn, the bed sheet is always on you. So you've kept more error tolerance, in that case. For example, you'll find people sometimes using very narrow pipes, and there's some scale formation, and it chokes up. And whenever you are suspecting that you may have that, it's much better to take a pipe with a larger diameter. These are some examples, and you can think of many such examples. Limit effects, like for example, if you do have a problem, can you contain that problem rather than it just spreading out? Like for example, if let's say of course the MIC got released, but suppose there was a way of in those situations that you could drain the bottom valve and let all the MIC actually go down into a reactor underground, then I might have been able to contain the release. So I can have a limited effect, or even take a simple thing like you are carrying, let's say, some bottles. It's quite common, you find people carrying bottles of some solvent or something from place A to place B, and they're just holding it by the neck, and if it breaks, or sometimes you can trip and fall. Okay? I mean, it can break. And then there are others who might actually put it on a tray and take it, so that even if by any reason it spills, it will spill inside the tray. Or you have a container for a big bottle, 5-liter bottle, and you hold it by the handle and take it, and in case anything falls or anything, it might fall inside that container. So, and this kind of thing, for example, is routinely practiced in the nuclear industry, nuclear power plants, because you simply cannot go wrong. I mean, so you'll have to have layers and layers of secondary and tertiary protection, mostly as an anticipation if something goes wrong. I mean, that's right there. Of course, I mean, there's a difference between limit effects here and simplify, because they might appear contradictory in some ways. But in one case, of course, you're talking about simplify by the type of chemistry that you do, which simplifies matters. Okay, so that's the kind of simplification we are talking about. And limit effects is really layers of additional protection just in case. I mean, so the two are not quite the same. All clear?
Yes, sir.
We have seen these principles. We talked about the process involved in making carbaryl, and I was just thinking that if you had to look at these principles of inherent safety, what might one be able to do with this process to make it inherently safer? Let's take a couple of minutes and try to write it down. Tell me the first one. What would you do? I've also included that CO plus chlorine gives you phosgene. Don't worry if it is wrong. Don't be inhibited. Many times, I find that you'll actually know the answer, but you're just a bit shy, just in case it is wrong, and you might feel a bit embarrassed. Don't bother about such things.
So as soon as we produce phosgene, we can immediately convert it to MCC because phosgene is very toxic. So rather than storing it, we can like directly convert it. That way, we will be following the first step, minimizing that is reducing the amount of hazardous materials present.
How brilliant! Why did you restrict it only to phosgene? Why not extend that principle to all the other steps also?
So we can extend it, but first,
right. So you can extend it.
Yes.
What was the product that they were selling?
Carbaryl.
Carbaryl. Okay. Everything else is basically there just to be able to produce carbaryl, right? Nothing else. Nobody has any love for MCC or phosgene or MIC, except that these were required to produce carbaryl. So exactly as you said, if you can produce and use. So I mean, why do I need these storage tanks? The moment I made phosgene, why can't I react it with methylamine and get this? Why can't I take this and directly carry out the next step and make MIC? And why can't I immediately make use of the MIC and react it with 1-naphthol and get carbaryl? Why do I need such huge amounts of storage? And I think you have been bang on. You've absolutely got it right. Everything else could have been produced and used up instead of accumulating huge quantities. In fact, let me tell you, the Bhopal accident was such an eye-opener that every company started looking at their processes and asking this basic question of minimize. I remember I had gone to visit a plant. It was part of the ICI group where I was working, and it was somewhere in Europe. I was visiting them, and they told me they were producing what? About 1 million tons of polyurethane, and one of the chemicals that they require is phosgene to make polyurethane. And they told me, Pushpito, in our plant, at any given time, we don't have more than 100 kg of phosgene. So they had made their operations continuous in a way that something is produced and something is used. So it is not just a hypothetical thing, and you understand how great this particular principle of minimize is. Let us also look at another example, and this is from Kletz's paper. How is nitroglycerin produced? What do you have to do to produce nitroglycerin?
So nitration of glycerin.
Right, nitration of glycerin. That's what you have to do. Now, glycerin as such is quite benign, and the nitrating agent, nitric acid, is also, I mean, hazardous, but not that hazardous. But nitroglycerin is an explosive, dynamite. Let me tell you, the same company ICI who had put up the first explosives plant in our country, my earlier boss, he was the one in charge of that plant. He was narrating to me one day that he had gone to the plant and he just came out, it was in Bihar. He just came out from that plant, and literally he says within a few minutes after that, there was no plant. It's gone. That everything, was blown up. Okay, there was a serious accident, and in fact, that was one of the accidents which propelled this kind of rethinking, on the process of making nitroglycerin. Okay, and effectively, similar kind of concept as produce and use, And so let's just read what it says. Probably the best example of the way in which the inventory of a hazardous material can be produced is provided by the modern nitroglycerin process as described by Bell. Instead of a vessel containing a ton of reaction mixture, the glycerin and acid are mixed in a tiny injector. The partial vacuum created by the high velocity jet of acid draws in the glycerin through a side arm. So that's how the stoichiometry was controlled. If the acid rate falls off for any reason, the glycerin flow falls in proportion without the intervention of any mechanical equipment. You can see that simplify, how it was beautifully simplified. The quantity of nitroglycerin present is so small that the operators can be protected by a single blast valve. Whenever you're making an explosive, you have to have one weak valve, it's a blast valve, so that that takes the shock wave and basically blows off, and then everything is out in the open. And otherwise, if it's a closed thing, now once nitroglycerin is made, if you absorb it in substances like Kieselguhr, that accidental detonation problem actually gets reduced, quite significantly. It's not eliminated. Nitroglycerin still can cause problems. So really then most of the problem with having large amounts of nitroglycerin is avoided by just having this injected and producing tiny amounts, and off it goes and it gets absorbed in the Kieselguhr, and you've got a relatively safer product. Whereas in earlier days, you took, as is written, ton of glycerine, a ton of nitric acid. I mean, what do you expect? Except that you'll have a problem. Okay, so I hope that you understand. In fact, it's quite interesting. Just as an aside, and I think probably some of you might know it. When Alfred Nobel was actually detested, he was hated, because many people got killed even after his invention. He was known actually as the merchant of death. There was a death of Nobel, and there was an obituary in the newspaper the next day, which said that finally the merchant of death is no more, is gone. Okay? But it was some other Nobel who had died, not Alfred Nobel. And so he read his obituary, and felt so ashamed. That is actually one of the things that spurred him to start the Nobel Prize, and it was really to be recognized for something better, than what he was being remembered for. Okay. So just and that happens, people of course forgot all the great things that happened because of dynamite, all the tunnels that you could make, the mines that you could blast, effortlessly, all that stuff. And people, of course, will remember only the tragedies out of it, and so that's the reality. So, but I just thought I'll mention this to you. Take another case. Now, this is not, those two examples were of minimized. Let us now look at substitute. I could not think of a better example. This is one of the best examples I found. It is from the Monsanto group. They actually got the US presidential award, in green chemistry. There was a challenge, and they won that in 1996 for a greener synthetic pathway for again, again a pesticide. This was a very, very important pesticide, let us say. Okay. Now the way it was being made, this was the crucial intermediate, DSIDA, the stuff, and then they have PCl3 with it, and in the presence of HCHO, okay, this reacts, right, and they get this. This part is not so unsafe, I mean, still not a great reaction, but still not so unsafe. Okay, but the making of this DSIDA is dangerous. It's made from what is known as the synthesis. So you take ammonia, take formaldehyde, and you have to take HCN. You know how poisonous HCN is. Okay? And then you have to cook these up. It's a gas phase reaction. Out of that, you get this. Okay? Not sure whether it's a gas phase or a solution reaction. It could have been done in solution also. Not very sure. I'll have to check this. And you get this. Then of course you hydrolyze the cyano group and you will generate the and neutralize and you will generate the CO2Na. Okay, so that's your DSIDO. The real impetus was to get rid of this process because it's absolutely dangerous. You can have something even worse than Bhopal if there's an accident. Now this is the thing. You can go in two different directions. You can someone will say, oh, I'll put an alarm for this, I'll look at passive safety, I'll do this, I'll do that, I'll put in another layer of protection. Yeah, you do all that and you make your plant costlier and more sophisticated. Okay, you keep doing that. But that there is another way to solve a problem. Yeah. Of course, when you don't have another way to solve the problem, of course, that's what you'll do. You'll have to put in those layers of protection. But what Monsanto did, they looked at this molecule and I'm sure they would have said, hey, this is, maybe I can start with diethanolamine. After all, what is diethanolamine? It's NH and CH2, CH2OH, you know. That's what it is. And so someone else probably thought that if I can do a dehydrogenation, and then if it tautomerizes, so I get an enol, you know, and then it opens up or it will basically convert into the aldehyde. No, I'll get so I have a dehydration, I get an enol, and then you know I can get a CH2CHO, right? And I can do that, right? And so it's just simple dehydrogenation chemistry. And if I repeat that, so I got CHO. And if I were to repeat that once more, you know, this kind of dehydrogenation, then next time I'll end up with an acid. So that's what you'll get. I'll get 4 moles of H2, you know, 2 from this side, 2 from this side, okay? And I'll end up with this. So they started doing research into whether one can identify catalysts which can do this. And they found that a copper catalyst does a good job of doing the dehydrogenation under alkaline conditions. Once you have got this, then of course, you know, the rest of the process is relatively not so difficult. But can you imagine the implication of this, you know, that it was so revolutionary that and everybody who was into glyphosate would probably have licensed technology from Monsanto besides them practicing it, and they made the world safer. The other very interesting thing is this reaction was an exothermic reaction, and so you can imagine that it will liberate heat, and obviously there is always a fear that it can blow up the vessel, just like it happened in the case of MIC reacting with water. This is an endothermic reaction. Of course, in the sense that an endothermic reaction is more energy intensive, it requires energy. Yeah, but then if I have to look at the pros and cons of safety and hazard versus a higher energy input, I may choose a higher energy input. I may say, no, I don't want this. And also, if I go into the life cycle analysis and not just start from here, but if I say, hey, where did ammonia come from? Where did formaldehyde come from? Where did HCN come from? And you go back, and maybe when you do the sum total, you'll find that no, it is not that it didn't require energy. It required a lot of energy. whereas this may have actually been advantageous even from that point of view. So this is a wonderful example of how one substituted process A with process B to make the same product, DSIDA. I didn't change the process from here on, no, but I substituted a hazardous process with a relatively more benign process. Did everyone understand the reactions?
Yes, sir.
Okay. I was just trying to see what would be the expectations from chemical engineers who are involved in industrial engineering chemistry. What are the kinds of things that you might have to do? And so I was just trying to compile this. One is work closely with chemists on process development, providing feedback and guidance on practical issues to reduce wasted efforts and accelerate pace of development. I've found this in many places. Okay, I mean, all the places where I was the director and heading organizations, that somehow there is this attitude that processes will be developed by chemists, and after they have developed these processes, they will hand it over to the chemical engineer, and the chemical engineer then will scale it up. But the process that I have developed could be not so good. What that chemical engineer will scale up, and why should he or she scale it up? So I used to find, in fact, in many cases, I introduced it also. I said, hey, you chemical engineers and chemists, you work together right from the beginning. So that if like, let's say chemist says, I identified a good process is this. Now you might look at it from a chemical engineering perspective of all the parameters that we discussed by which you can judge a process, and you might say that's great, but I think it will be difficult to implement this because of reason A and B and C. So can you just change it a bit? Rest of it looks okay, but this one I think if you can change, it will be great. That kind of feedback, and if I have a learning mindset, a positive mindset, I will say, yeah, that's fine, I'll try to do it. Now, I also know why they don't do it. The reason is because most of the processes will fall flat. There wouldn't be so many thousands of papers in journals if you had got that feedback to begin with. What most people tend to do is they sweep under the rug anything that is uncomfortable. And they just tell you half-truths. Because otherwise they can't publish their paper also. They may not get their increment if somebody says, hey, did you develop a process? And you say, no, I did, but the chemical engineer shot it down and I have to do it all over again. Everybody tries to protect their turf. Chemical engineer also, many cases it might mean that you have to also learn a bit of chemistry, and you have to also have a positive attitude. You cannot only shoot down something and say, hey, this doesn't work, that doesn't work. You also must try and make it work. It's not that your attitude is one of just saying no to everything. No. You help in the process. For example, most chemists, when they're developing processes, they have no idea about the thermodynamics of the process, or many times of the kinetics. I mean, of course, gross kinetics, you might know that I carried out the reaction for 10 hours. After that, I worked it up. I got 90% isolated yield. That kind of thing you will know. But that's not kinetics. You may want to understand the orders of reaction, get to the mechanism, what is the rate limiting step. So many things, there's to know. And I can improve things. I can understand safety. There are reaction calorimeters. You can actually carry out a reaction and you'll get all the data over there. And so it would be so wonderful to know all this. Or in your fourth year, when you're doing home paper, most of the time I see students will say, sir, I could not get any data on thermodynamics or on kinetics. Can you help? And it means that many times, either it is a trade secret, the people who have developed it have kept it to themselves. And in fact, that happened. Like recently, one of my students wrote to BRC about process and said, I liked your process, but I don't find any thermodynamic or kinetic data. And the guy from there wrote back saying, these are import substitute chemicals. You will not get this data. Obviously, chemical engineers have a better training in these areas. Also, you must be able to, when you're scaling up, all right, you must be able to scale it up and assess the robustness of a process. If it is very finicky that if I change the temperature by 5 degrees here and there and all hell breaks loose, then it's not a robust process, and so it has to be made more robust. So that kind of understanding of robustness while you're scaling it up is extremely important. Plant design. How do you design the overall plant for carrying out this kind of process? Simulation. Every time I don't need to do experiments to generate data. I may be able to simulate. What if the water gets cut off? What will happen then? What if suddenly the power goes off? What will happen then? What if my reactor breaks? Or if I'm doing it in the laboratory and there's a crack in my down bottom flask? What happens? What if there's a pressure buildup? So what if? And do you have an answer to those? If you don't have an answer, just build in the answer. That's all. What are the opportunities to save energy? Can you think of heat integration? Or everything is independent of each other with no integration? Is it like that? A chemist who is developing it may not be so concerned about saving energy. But you would, and the management would, because at the end of the day, it's so important. Are you able to get your product with the desired specification? I see this, and numerous people used to, we did this, but now the consumer is saying this specification will not do, it's off spec. Are you able to obtain products with the desired specification, or does it require a lot of reworking? So these would be very, very important things. And how do I minimize the need for reworking of a process? Another, many times you set up a plant. In fact, some of our ICT professors have done a wonderful job in this, even for companies like Reliance. I used to have a person who was working with me who did a terrific job of debottlenecking a plant. Now, what happens is, many times, you have a plant and you study it and you say, this is not what's limiting me. Suppose I'm producing 5 tons a day. And I say, oh, it is this step. This step is the one which is holding me up. And if I can increase the capacity for this step, then the rest of the step, I don't need to increase my plant size. So it's not as if I have to double everything to be able to increase the capacity by 2. And that is the kind of debottlenecking or being able to raise the throughput, that from the same plant that I'm able to churn out more product. Because obviously that will cut down on capital cost per ton of product. And that kind of capital is a difficult resource to get. You may want to look at all the opportunities to reduce the input costs. Can I recover solvents? Am I doing that? What is the efficiency of recovery? Okay, so all the kinds of things. Can I look at the specifications of raw material and maybe source it from a cheaper source, and what would be the implication of that? Like, for example, what do you think is happening in many places? They are instead of buying crude of a good quality, they go and buy junk crude, because they're getting it for cheap. Okay? But you don't know what is the implication. They might be creating huge amounts of waste, toxic metals, or what have you. Of course, I can reduce input costs, but I'll have to also have a look at that. How do I deal with the problem of impurities or contaminants in my raw materials? How do I minimize waste? How do I ensure that I have environmental compliance? And how do I have an eye on green manufacture? Be it energy, be it the water footprint, the carbon footprint, the environmental footprint, other ways. Okay, so all of these could be extremely important areas for a chemical engineer. And also identify opportunities for process improvement based on learning from the plant. This is so interesting because I used to find many times the best ideas came from chemical engineers who, based on their experience in the plant, they gave excellent suggestions that there is an opportunity to, I found that you can do this instead of that, and there's a huge advantage. And it comes only at the plant level. You know, when you're doing things at a certain scale, some of these opportunities might become a bit clearer. Another is that today, in all of technology, and especially driven by sustainability, understanding of product life cycle is vitally important. You can't just start, as I showed you, you can't just say, I'm starting with ammonia and HCN and formaldehyde. You have to ask, hey, where did this come from? What raw materials were used in producing them? And so I am getting the footprint at each stage. You know, and I'm going all the way back to the most basic things. And likewise, once I've used my product, what happens after that? Like my battery has died out, and what will I do with the battery? Most of the people, you'll find their mobiles are sitting at home, you know, the old mobiles. And while we are trying to get more and more lithium from somewhere, but if there was a way of recycling that battery, that would be great. I might be able to recover lithium, I might be able to recover cobalt. And otherwise, these things many times can be treated as hazardous waste. I have to actually pay money to dispose of those. So that is what is meant by a cradle to grave approach, that your responsibility does not end simply because you produce the good. The question is what happens after that, all the way till finally our disposal is achieved of that substance. And wherever I can recycle, wherever I can make use of waste, convert waste into value, that would be all extremely important. You saw during the Industrial Revolution the kinds of products that were churned out by chemists and the chemical engineers. What a phenomenal range of products they created. Now, this is something from 2009, and it was created by the Wharton School in University of Pennsylvania. They had a questionnaire and they gave it to many people and asked them to say what are the top 30 innovations of the last 30 years. Basically going up to maybe around 1980. It is instructive that if you look at what they identified, most of the things, and I think we will also agree that things like internet, broadband, etc. are so used, the PC, the laptop, the mobile phone, the email, etc. I don't think too many people would argue that no, indeed, these were great innovations. You have to ask yourself, hey, where is chemical technology in all of this? Of course, there are some which are obvious, like biofuels. I told you that in photovoltaic solar energy, for example, how you make the semiconductors, and many of the material science, all of these ultimately depend on some materials. So what you'll find is that the role of the chemical engineer and the material scientist may be more at the back end, not necessarily at the front end. And so people might say, oh, you have had a role to play in this. If you ask someone, you say, yeah, I have. They say, what is it? I thought only the biofuels, it looks a bit more like some chemical. You can say, what about fiber optics? I mean, it is developed through chemical processing. Okay? Or a light emitting diode. Do you think that there was no role of a chemist or a chemical engineer? That's not true. Okay, but the truth of the matter is, okay, that you simply do not see the kind of presence of chemists and chemical engineers at the front end that you had, for example, in the golden era, something from let's say 1850 to 1950. I mean, it was really huge. All the polymers got created. I mean, all the medicines got created. Of course, medicines are created even now. All the dyes, everything. You just name it. Okay, it was all created there. The question is that has the pace of breakthrough in chemical technology slowed down? Are we less innovative today than what we were maybe 100 years ago? My feeling is, of course, if I tell someone, they won't like it. But my feeling is, yeah, that is the truth. Okay? That actually we have not been that innovative, as the people, and there are various reasons. Earlier, people could experiment left, right, and center, do all kinds of, try out all kinds of things, because safety was not such a critical issue. Today, if you go to try something, and especially in an industry, especially in Europe or USA and all, they will ask you, hey, what are you trying to do? And if you say, I'm just trying out this, there's nothing doing. You first go and identify the hazards and risks in the process before you can do anything. And so you are not that free today to do as you wish. And that's, I think, one of the reasons why innovations have come down, because chemical technology is probably one of the riskiest. So that has had an impact. And the second is that, earlier days, there wasn't so much of a distinction between who is a physicist, who is a chemist, who is a chemical engineer, who is a mechanical engineer. They were all working towards doing something. Neither was academia so snooty to only think that they will do all hi-fi things. It wasn't like that. There was very, very strong interaction between industry and academia. I told you about ICI when they invented polyethylene. Actually, they didn't even know what was going on, and they went to one of the professors in Oxford, Hinchelwood, and took his help and figured out what had happened. That is what gave birth to polyethylene. That is the level of interactions that there were between academia and industry. Not this reverse thing, this is available, you can get it from abroad, it costs 1,000 rupees. Can you make it for me in 500 rupees? So that's one kind of interaction. Many times academia gets put off by those things. And also, it's not so easy to do. But at the really path-breaking end, where is that interaction between industry and academia? For that, you need brilliant people like you in industry who can identify and say, hey, this requires fundamental research. This will require scientific understanding. We don't have it in our industry. You have to go to academia. As I said, the appetite for risk-taking has gone down. There is too much of emphasis on short term. Academia is excessively on long term, and they have no idea about short term many times. And industry is so short term that many times you cannot work and do something great in that time scale. They'll give you a pat in the back. Everyone will say, yeah, great, But you just still do the thing that is already known. Finally, the bottom line is that, yeah, I heard you, all that is fine. And I hear that even in academia, forget about in industry. I find it's all many times reverse engineering. But what has happened is, if you look at all the processes today, there's no doubt that they're much more perfect than what they were in the past. And how has that happened? I think it has happened because of the role of engineers, primarily. I think engineers have really done a great job of sense all the things which require greater levels of precision, higher levels of robustness, and they make things more perfect. And the emphasis of chemical industry has shifted, partly also because when you are going into millions of tons of production as compared to thousands of tons, I cannot do it without being perfect. I can afford to be not so perfect when I'm making a few kilograms of something. Can I do that when I'm making millions of tons? I can't. And so that is what has given greater opportunities to engineers such as yourselves to make a much more important contribution. Every time you need not create a new pesticide, but if you're smart enough that you can make DSIDA in a by a different method or prevent MIC buildup, great, you've done your job. Another, of course, area is all innovations are likely to be increasingly centered around sustainable development. You might require new energy sources, new feedstock. We might have run out of feedstock, process safety, product safety. All of these things are going to have a huge impact. And let me tell you that if you are like a horse with a blinder, you will be left by the wayside. The ability of people to look at artificial intelligence and to say what is the role of AI in future chemical processing, what is the role of robotics, what is the role of this, what is the role of that, what is the role of material science, what is the role of biology in processes. If I can increasingly spot developments in allied fields and maybe partner with them or at least learn from them, then I think these are the kinds of things that will lead to new breakthrough. So with that, I have come to the end of the introduction. Any questions up till now from any of the any part of the introduction? All clear?
Yes.
Now onward, we will be actually very product focused. We will look at some of the important chemicals that are manufactured by chemical industries, and we will cover those. What is the process? What are the evolution that have taken place in the process? What is being practiced today? Has it always been like that, or has it changed? And why did it change? So those are the kinds of things that we will try and look at from now on. Now, one of the largest chemicals by volume is sulphuric acid, H2SO4. I just got this data yesterday that last year it was about 200 and close to about 257 million metric tons. But you know, it was also a pandemic year, so maybe there was some decline in production, and perhaps it would have been a bit more if it had been a normal year. But still, you can imagine how large it is, 257 million tons. Out of this, the bulk of it, I think close to about 60 to 70% goes into the manufacture of fertilizer. You have seen, for example, you can react ammonia and sulfuric acid and you get ammonium sulfate. Later on, when we cover phosphate fertilizers, you will see that the principal reaction is the reaction between phosphate rock and sulfuric acid, and that consumes a huge amount of sulfuric acid. Then you go on to things like hydrofluoric acid, which you get from fluorite rock, like CET1502, which you treat with sulfuric acid, and you end up with hydrofluoric acid. You know? And HF is a very, very important chemical. You also know that in all the sulfonation processes, sulfuric acid is so important. So it's not just in making inorganic compounds, but also in many of the organic compounds. The lead acid battery, sulfuric acid is, of course, at the heart of it. So much of mining, leaching of metals from ores in the paper mills, you use sulfuric acid. So huge application, and that's why you require such a large quantity. Now, this is the global scenario. Now, I found that the global scenario has actually changed a bit from 2012. There was a similar pie chart from 2012. If you see, the largest consumer, more than a third, is China alone, mainland China. The next is North America, which is a large consumer. You have Africa also quite big. That is because of a lot of the metal mining. Africa is very rich in metal sources. So that mining industry takes up a lot of sulfuric acid. And then you have got Europe. India is now part of this other. Whereas in 2012, India was shown as a separate, you would see how much was the consumption in India. So it looks like what has happened is that there have been huge changes. For example, a lot of the manufacturing of phosphate fertilizer is not done in India today. India is importing. So it's being manufactured somewhere else and we are importing, and so we have got more into trading activity. Or maybe we buy phosphoric acid and then react it with ammonia and make ammonium phosphate. That's about what we do today. Okay. So whereas that was not the case 10, 12 years back. Okay. So there have been massive changes that have taken place, but if anything, China, for example, has consolidated its position. So even in 2012, it was very big, and even now, in 2020, if anything, they have grown a bit more. This is actually a reflection of the amount of bulk chemicals that we are producing or consuming. That what exactly are we involved in? What are the kinds of activities that we are doing in India today? It'll give you some idea. The other thing is that although we say sulfuric acid, concentrated sulfuric acid is 98% sulfuric acid, but you also know that there are certain applications, like if you have to do sulfonation chemistry for some of the organic molecules, you actually can only do it with very concentrated sulfuric acid like oleum. Okay? Oleum is where I take concentrated sulfuric acid and have to pass more SO3 into it, and I'll form oleum, and it becomes extremely reactive then. And so under those conditions, certain organic reactions which are otherwise very difficult to do, you might be able to do. And in fact, this was one of the reasons for a technology shift in the manufacture of sulfuric acid that took place over the years.
So the pie chart was for the overall consumption of H2SO4 or the overall production?
I'll just check this out, whether it is for production or consumption. I think that's the question you're asking, right?
Yes, sir.
I think this is the market for sulfuric acid. So probably more related to consumption, but I'll just check it out.
Thank you, sir.
What is the main feedstock that you require to produce sulfuric acid? What do you need? What's the most important feedstock?
Sulfur or sulfur dioxide.
Very good. Sulfur or sulfur dioxide. Brilliant. Sulfur is, of course, the most basic. In earlier days, it was really all based on sulfur. There were mines, which were available. These were mines of sulfur. There were sulfur deposits, but it was underground, so you had to take it out. And in fact, I think the one of the earliest was a mine in Louisiana, where 1867. You can see about 150 odd years back. That they were actually taking out sulfur, or 1903 was when they started the process, and it's by a process known as the Prash process. And then once, of course, I get sulfur, then I can convert it into sulfuric acid. Sulfur is of course a solid. It exists as something like SA8. So those would be some allotropes of sulfur. How would you take out sulfur from the ground? What would you do if you knew that there is sulfur, but it is maybe 100 meters down or maybe a few hundred meters down?
Uh, so just like we do fracking for oil, we can send a pipeline with a
Yeah.
material that can dissolve crystal or solid sulfur, and we can make a system where it absorbs back the dissolved liquid and brings it out, and then we can
So
separate
you
it.
will pump some solvent, right? Is that what you're
Yes,
saying?
yes, sir.
Huh? Very good idea. Let me write it down. Inject a solvent in which sulfur dissolves. Any other idea that you have?
So maybe a pipe in the similar way with activated carbon attached to it so that sulfur adsorbs onto it and then it can be pulled up.
How a solid will adsorb on a solid? It's a solid.
Okay, sir.
Anything else?
Sir, lifting it by a pulley.
Very good idea. One of the things you need to understand is that when you are drilling, say you drill at a point.
Sir, I am saying that from the distance where the chemical must be extracted, from that distance we can put steam and push above the chemical which is being extracted.
Okay, that's great. Your moral is there. You're saying push steam to displace sulfur. Now, can you push steam and displace a solid? Do you think it's possible?
Sir, it will be difficult, sir.
It will be difficult, right? And secondly, another thing that you need to see is that when we drill a hole, that's a small area that we are covering, whereas the reservoir could be much wider, much larger. Like when I drill, it's not as if the oil is just present where I've drilled my hole. Okay, the oil is present all over, and it will come out from all over. So, so if I'm just focused on that, could be the same problem with the pulley. I would be able to take out only the solid, which is right there. But what about all the vast adjoining area where there is sulfur? How will I pull that out? I can't.
Yes, sir.
Right? Clear? Huh?
Yes, sir.
But your idea of steam is great. Now, the first thing that you should look at in this kind of a situation is what is the melting point of the stuff that I'm trying to take out? Can it be melted? And sulfur can, because sulfur has a melting temperature of only 115 degrees. So I can convert it into a liquid at 115 degrees centigrade. And steam, superheated steam, I can get at 165 degrees centigrade. So it's true what you said, you push steam, but what that steam will do is that it will liquefy the sulfur and it makes your problem that much easier. You got it?
Yes, sir.
Okay, but still, sulfur is quite heavy. I'll have to check the density of molten sulfur. 2 grams per cent. You can see how dense it is. Even molten sulfur. So not so easy. Density 2 grams per centimeter cube. So very dense. It's not like water and oil, which is even lighter than water. So I can melt it. But to displace it, then I'll have to inject something which is even has a higher density to be able to displace it. Okay. So which is going to be extremely difficult. Whereas in the case of oil, you use brines. Okay, brines are cheap stuff, and I can get a density of say 1.3, etc. and so it becomes easier to displace that oil by injecting brine. Will be much harder to do with sulfur, but I have melted it, okay, because the melting temperature is not so high. Now let's ask the question, okay, so I have suggestions to lift molten sulfur to the top, considering that it has high density. Any suggestions?
Sir, pump.
Pump it out. Pump that 2 gram per centimeter cube liquid out. That's what you're saying, right?
Yes, sir.
Pump the high density molten mass out.
Sure, we could just pump a lot of froth. We can create a lot of froth because
Create
of which
a-
the sulfur will
create
froth. So bubbles kind of.
Oh, wonderful! Create froth. Wow!
Which carries the sulfur above the
Create froth to increase
lift the
buoyancy,
sulfur.
right?
Yes, sir.
That's what you are saying.
Yes, sir.
Brilliant! You have actually discovered the technology that they use. What is done is that you first pass superheated steam, so you melt the sulfur, and then through another pipe, you actually introduce air and maybe some amount of surfactants or something maybe also used. I'm injecting the air and it gets trapped in the sulfur. Why? Because sulfur is quite viscous. It can froth up and it can trap the air, and because of that now it rises to the surface. And I've obviously lowered the density sufficiently that the steam which I injected, it can then displace the sulfur and the sulfur just lifts up. Clear?
Yes, sir.
Yes, sir.
Okay. You can see that in all industrial processes, there is invariably some ingenuity. Industrial processes are never routine and boring. There's always some smartness. The sulfur that you get out is very pure, 99.7 to 99.8% pure sulfur. This used to be produced even in 1989. You can see something like close to 4 million tons in the US and something like 1 million tons in Mexico. And look at the depths. They could even go up to depths of 800 meters. You're talking about close to a kilometer depth. You can work out what is the energy input in doing all this. But today, what has happened is that this technology has become pretty much abandoned, except for in a few places like Poland and Mexico. They still actually produce sulfur this way, because Poland also has large salt domes, just like in Louisiana, and the caps have sulfur. That's what they do, and Mexico does likewise. But the rest of the world is now getting their sulfur from somewhere else. Can anyone tell me where the rest of the world is now getting its sulfur from?
Volcanoes?
Wow. No, not really. I mean, it would not be a reliable feedstock.
So lead sulfide, sir. Ore.
So you are talking about sulfide ores. No? Okay. Very good. There are large deposits of pyrite ores. Iron pyrite is FeS2. Pyrite has a very interesting property that if you heat it, one sulfur gets released, and at the temperature at which you are heating, it becomes liquid and can be taken out. But it doesn't release both the sulfurs. This patent you can see from 1959 talks about a method of roasting pyrite where first, of course, they roast it in a way that one sulfur comes out and it's taken out. And it says that heated bed of dense fluidized inert material through which gaseous products of reaction in said bed move at the temperature to liberate the labile sulfur atom from the pyrite particles fed to the bed. So the first one is taken out. Now they pass oxygen through it, okay, oxygen or air. In the presence of that, what will happen to the FES at high temperatures?
The oxygen would
SO2O3.
displace the sulfur and then it would even react with the sulfur. So we'll get iron oxide
Yeah,
and sulfur
it will
dioxide.
react. FES will become Fe2O3. It'll get converted into ferric oxide, and the sulfur will react with the oxygen and become sulfur dioxide. Okay?
Yes, sir.
You do it in two stages. Use a fluidized bed so that these fine particles of pyrite, they're just floating in the bed. And that way what you have is a very intimate contact between the hot air and these particles. And so that reaction is facilitated. So one part you'll get out as sulfur and the other part you'll get out as SO2. I could use the sulfur itself as my feedstock to start my contact process, assuming you are doing the contact process, or I could start with SO2. There's no need to convert SO2 back into sulfur again. But today, even the pyrites have been phased out. There's very little production from the pyrites. There is another source. Can anyone tell me what might be that source? And almost the entire production is now based on that.
Petroleum, burning of petroleum would release SO2.
Brilliant. But don't wait to burn the petroleum. You recover the sulfur before you burn the petroleum. Wherever possible, try to recover at source. Correct? That would be a better approach or not?
Yes, sir.
And you have heard about all these GS specifications for fuels now, and we are talking about going into BS6, where the sulfur level has to be very, very low, because one of the biggest concerns, biggest problems with vehicular emission is because of sulfur, and the particulate matter that you get. Everybody is removing the sulfur from the crude oil, and crude oil has a fair amount of sulfur. So that is done by a process known as hydrotreating. So I take crude oil and I treat it with hydrogen gas, and that is hydrotreating. So what will happen if I react crude oil with hydrogen gas? What kind of a sulfur compound am I likely to form?
Hydrogen sulfide.
Hydrogen sulfide.
Wonderful. Hydrogen sulfide. That's what you'll get. So the way in which today almost all the sulfur is obtained is really from crude oil by the hydrotreating process, which forms H2S. Okay? The H2S then is reacted with oxygen. This is known as the Claus process. Okay, CLAUS. And in the Claus process, what you get is you get SO2 and water. You can note the temperature 850 degrees centigrade. Have a look at the delta H. It's unbelievably exothermic. Because of this high temperature, all of the H2S is not converted into SO2. The reason is because at that kind of a temperature, my equilibrium would be towards the left because of the thermodynamics of the exothermic reaction. So quite a bit of H2S would remain unreacted. What then happens is very interesting. I have partially formed SO2 and some amount of my H2S is unreacted. We have seen this kind of thing before. We have looked at disproportionation chemistry. We saw it with the ammonium nitride. which form nitrogen. This is a standard thing which is done in so many places that I can do reproportionation chemistry. That is, things which are in different oxidation state of the same element, that they can react with each other and it can reproportionate. So if I react H2S with SO2, what could be a possible product that I might make? One is in a very reduced state. What is the oxidation state of sulfur in H2S?
-2.
Wonderful, -2. And in SO2?
+4.
+4.
Right. So if, let's say, I have to get sulfur out of it, how many H2S I need to react with how much of SO2?
So 2.
Right. 2 H2S plus SO2 will give me 3 sulfurs. And that's what you have, the equation. 2 H2S plus SO2 gives 3 sulfur. It's a highly exothermic reaction also. So what happens is that even though I can push the equilibrium to the right by effectively this subsequent reaction, unfortunately, because this also is very exothermic, so I cannot push it all the way to the right. So what will happen is that typically it forms an incomplete reaction, and out of 10 H2S, roughly about 7 end up as sulfur, and you'll have 3 out of 10 being present as 2 H2S and 1 SO2. So it's incomplete. And it's incomplete because of the high temperature at which I'm doing the reaction and because the reaction is exothermic. Since I have this now, what can I possibly do to try and get 10 out of 10, all 10 H2S will become sulfur? So what, from your knowledge of thermodynamics, what do I need to do?
So remove it from the system.
Yes, one is, of course, I'm removing. Of course, the sulfur which I get, I will take it out.
Sir, moderate pressure and temperature.
I can push the equilibrium to the right by decreasing the temperature. So what you do is the Claus process is done in 2 steps. The first is a thermal process where most of it forms sulfur and I take it out. And then if I have to do this now with a lower temperature, what might I additionally require if I want to decrease the temperature?
Coolant or a cooling system.
Huh?
Yes, sir.
No, of course I'll be doing that. I'll get the cooling system, I'll reduce the temperature. But what might happen to the kinetics?
Slow down.
So if a reaction slows down, what should I try and do?
Sir, add a catalyst.
Catalyst.
Wonderful. Okay. You see, everything you came up with answers. I didn't. So there is a catalytic step of the Claus process in which the reaction is carried out at a lower temperature and it is carried out in the presence of these as catalysts, which were identified alumina, Al2O3 or titanium. These were found to be good catalysts for reducing the reaction temperature, and that way the entire thing I can do and I can get a recovery of something like 97% of the input sulfur in the form of H2S can be converted into sulfur element. And that is the brilliance of all this engineering. Any questions from anyone?
In the Claus process, which catalyst did you mention? So Al2O3 and TiO2?
Yeah, either or, not both. So I will continue with this tomorrow.